Okay, good afternoon, everyone, or good evening, good morning, wherever you are watching this presentation. Firstly, thanks to Rob for the introduction and also the organization committee for providing me this opportunity to speak here today. It would have been nice to come in person, but hopefully next time I can join you all in Vienna or wherever it is. So the basis of this presentation is based on work that was conducted over the last 1.5 years or so. And even though it's not directly related to the application of multi-level Monte Carlo to uncertainty quantification, I hope and believe that some of you will be interested in it because what I am going to discuss, in my opinion, does have many applications to various aspects in UQ, such as state estimation, but also parameter estimation as well. And so for this presentation, I'm going to consider, as I've slightly mentioned, the application of multi-level Monte Carlo to stochastic partial differential equations. So I started to understand and learn about the theory of multi-level Monte Carlo over the last few years or so. And from doing various different topics, I started to get an understanding that there has been some limited understanding or application of this to stochastic partial differential equations. There has been a lot of work done on UQ applications, on random PDEs, and also stochastic differential equations. So what I hope to show you from this presentation is just some recent work which really tries to understand this connection better between MLMC and SPDEs. And this is really the idea that we have really is trying to improve complexity rates in terms of the MSC to cost, where we exploit and use somewhat recent methodologies developed by Jensen and Kloden, which is the Exponential-Euler method. And so this leads to today's title of the presentation, which is Improved Efficiency of MLMC for SPDEs, Strong Pairwise Coupling. So this is joint work with a number of individuals, Håkan Hull, who is in the audience, who is based at the University of Oslo, AJ Jasra, who is at KAUST in Saudi Arabia, and Georgios, who is based at the University of Crete. So this presentation will follow pretty much the exact same outline and material as the paper that you see at the very top, which was archived in about September or October in the previous year. And the general outline that I have for this paper will follow exactly what I'm going to present today, which is that in the beginning, I'm going to discuss very briefly a primer on multi-level Monte Carlo. From this, I'm going to discuss some of the applications which it is being used for, in particular UQ-based applications, which will provide a motivation to try and understand this in terms of stochastic partial differential equations. I'll then provide a basic setup for the SPDEs, or the class of SPDEs that we consider for this presentation, and then discuss the actual methodology which is used for the strong pairwise coupling. And then at the very end, I'm going to show you some numerical experiments which really verify the improvements that we get through this form of coupling, while concluding with some final remarks and future research directions. But before I get on to the presentation, two particular papers that I want to highlight, which are very much used and are really based on the work that you see at the very top, are the two works that you see below this black line. So as I mentioned, the strong pairwise coupling, which I will get into in more detail in the presentation, is really based on this paper by Jensen and Kloden, which really provide improved rates of convergence related to stochastic partial differential equations, or a particular class of stochastic partial differential equations. And this will act as the primary motivation for our work. But as well as this, I also want to highlight a more recent paper done by Chernov and co-authors, some who are in the audience, where this is the first paper to my mind which really uses the ideas of Jensen and Kloden in a multi-level setting. The only difference is that the paper that you see at the very bottom is specific to data assimilation, in other words, Kalman filtering. So what we are going to do in this paper and presentation is to negate or really not consider any form of data assimilation or UQ, but just to consider that of stochastic partial differential equations. So I know that this is a conference and a workshop based on multi-level Monte Carlo, and I don't want to bore you with the details because most, if not all of you know everything what I'm about to say in the next few slides, but I felt obliged to at least mention this so it paints a picture for the presentation. So the idea of multi-level Monte Carlo was introduced by various authors, for example, Mike Giles in operations research, which should be 2008, not 2006. This is a small typo. But also earlier work of Hendrik going back to the late 90s and also the early O's. And for a very comprehensive understanding or general understanding is also Mike Giles' Act in America paper, which was released a number of years ago as well. But rather than going into the full details of what multi-level Monte Carlo does, I felt obliged and I felt it necessary just to give you a one-sentence aim or definition of multi-level Monte Carlo, which is to say that it is aimed at reducing the cost associated with a Monte Carlo algorithm while maintaining a particular order of MSC, which the order is of epsilon squared, where epsilon is greater than 0. So in other words, if you have a particular Monte Carlo algorithm that you have for whatever inference problem that may be, the idea is that if you apply multi-level Monte Carlo, you can reduce the cost to attain a particular order of MSC. And of course, given this definition, or this idea that I've already stated, can have a wide array of applications because of reducing the computational complexity. And so just to give you a few formal equations to really set the scene, let's consider the case if we want to approximate, let's say, some distribution, which I'm going to denote by pi of r of I, which is just given by some expectation. So we can be interested in computing some distribution or some quantities of interest, for example, the expectation. But of course, in many scenarios, this actual quantity, pi of r of I, is intractable or can be quite difficult to sample from. So what we can do instead is consider a case of discretizations related to approximations given by pi of L, where L represents the level of discretization. And as we all know, what we can do is actually represent this series of approximations through this telescoping sum that you have right here, where L denotes the finest level of discretization, and 0, of course, represents the discretization level of L equal to 0. And so what we can do from this is represent this approximation just through this telescoping sum right here. And this notion of this telescoping sum that I've mentioned is exactly what we can do in the multi-level setting, where we use this telescoping sum idea, and what we can actually define is a multi-level estimator related to approximating this pi of r of I, which is just given as this second equation that you see right here. So it looks almost identical to the first equation, except with a slight change in notation, but we also have to ensure that we have to define particular samples at each level that we have, going from L equals 1 all the way up to L equals capital L as well. And so with this, if we have the multi-level estimator given by pi of L, and we have the actual quantity that we're interested in approximating, then of course, in numerical analysis or even statistics, it makes sense to quantify this difference, at least in terms of a mean square error, which I've given as the very bottom equation right here. And as all of you know, we can decompose the MSC into two terms, a deterministic bias and a statistical bias, where I call the statistical bias the variance in this case. So the deterministic bias corresponds to the discretization related to the model of interest. And of course, because we're dealing with a Monte Carlo method, we also have a statistical bias, which I call the variance itself. So by applying multi-level Monte Carlo techniques, as we see from the right-hand side, the only difference that we see from modifying this to the usual estimator is that we see a difference in the variance term. So the bias remains the exact same by applying this multi-level estimator, but the difference that we see with multi-level Monte Carlo is through the variance. And as a result, you can think of multi-level Monte Carlo as being a variance reduction technique, where the difference actually comes in the variance and not the bias. And so with this original work presented by Mike Giles in 2006, he presented a well-known complexity theorem, which all of us have really used and modified depending on what application or what setting that we have used. So this general complexity theorem, I'm not going to go over the full details, but the general idea is if we have various constants given by alpha, beta, and gamma, which can represent the weak rates of convergence, the strong rates of convergence, and of course related to the cost itself, then if we are interested in targeting an MSC of order epsilon squared, then the cost related to this is just given by these complexity rates between the cost and the MSC, where this last rate that you see is what one would usually expect, at least for the usual single-level Monte Carlo scheme. But by applying multi-level techniques, it's very common to go to attain better rates of convergence, or complexity rates in terms of this particular rate, or even this rate, which is known as the canonical rate of convergence. So this is just the usual complexity theorem that we all know related to vanilla multi-level Monte Carlo. And so since the original work of Giles in 2006, there's been a huge list of applications and various new works that have been done, too many to name on one particular slide. But what I felt obliged was to actually give you a number of different interest and research directions, which are more related to both forward UQ and also inverse UQ. So the very first application, which TC has sort of alluded on, is really the application of Bayesian statistics, or let's say various methodologies using Bayesian statistics, such as Markov chain Monte Carlo, but also particle filtering methodologies. So a lot of the work that has been done in this particular field of Bayesian statistics is really down to the work of AJ Jasser and Cody Law, where they have really applied these multi-level techniques to an array of Bayesian statistical methodologies. This includes multi-level sequential Monte Carlo samplers, multi-level particle filter, also multi-level particle MCMC methods. And there's also been some work, original work done by Rob, Andrew, and Aretha, who actually worked on multi-level Markov chain Monte Carlo. As well as this, which is quite related to the idea of Bayesian statistics, is also using multi-level techniques for parameter estimation or inverse problems. And some of the original work done by this was done by Viet Huang, Christoph Schwab, and also Andrew Stewart, where they have a number of interesting papers which were published in inverse problems around 2011, 2010, and 2012. I don't remember the exact date, but it was around that time before I began my PhD, where they considered trying to understand theoretical aspects of applying multi-level techniques to inverse problems. But since those original works, from a theoretical point of view, there's been a lot of application-based papers trying to understand or reduce the complexity with multi-level Monte Carlo for Bayesian inverse problems, something TC just also discussed in his previous paper. This has also been applied to other ideas related to multi-level quasi-Monte Carlo. So these are two particular applications related to UQ and also related to my own research, but also, which has also been of interest and has really started to be looked at less so, but it was more popular, in my opinion anyway, in the early O's and late teens, was really the application of forward UQ, or the application of multi-level Monte Carlo to forward UQ. And this was really looked at for UQ solvers, at least for random partial differential equations. So for example, the stochastic collocation method, which was looked at quite readily. So a lot of the work, original work done by Raul Timpone, Fabio, and also Clayton, they looked at a lot of original work by this, and various other UQ solvers related to this have also been done. More recent work, at least done in the stochastic differential equation setting, has also been done for expected value information, and also applications of financial mathematics related to stochastic differential equations, which Al discussed earlier today in the conference itself. So the purpose of this slide really is to give you, which all of you know, a very big indication of the huge applicability of multi-level Monte Carlo. And there's a lot more applications, which again are too many to mention on one particular slide. But based on all of these applications, and especially based on the work that has been done on this, a very obvious question, which people may have, but I had in my mind at least, was what potential extensions could be made to stochastic partial differential equations. So there has been some work done on applying multi-level Monte Carlo to stochastic partial differential equations. But to my mind, most of the work that has been done on this has really been done from an analytical point of view and theoretical point of view. There hasn't really been much done related to the actual computation or numerical point of view. And this is really the basis and motivation behind this presentation, where we're really trying to get an understanding of applying multi-level Monte Carlo, especially to challenging SPDEs. And what I mean by challenging is really nonlinear stochastic partial differential equations. But before I discuss what has been done and the actual contribution of this work and the presentation, I'm first going to give you a general setup of what this presentation will include related to the SPDEs. So the class of SPDEs that I'm going to consider for this work are semi-linear stochastic partial differential equations, where we have a number of quantities of interest in this actual equation. We have an operator A, which I assume to be linear, given by this particular expression right here, where we have some Fourier basis functions, and we also have some sequence of numbers, which you can think of as being as the eigenvalues, just given through this equation that we have right here. As well as this, we have a nonlinear term, which is given by f, and depending on how you choose f, this can be a specific choice of a stochastic partial differential equation. And as well as this, we have a Brownian motion, which is given by w of t. But specific for this work, I'm going to say that w of t is a q Wiener process, or in other words, it takes this particular expression right here, where q of n is just, again, a non-negative sequence of numbers, which actually relates this lambda k that you see right here. But I'll get into the details of that later on related to the numerical experiments. So a very obvious question from this is, why do we consider the class of semi-linear stochastic partial differential equations? But there's really two reasons for this. The first reason is that the underlying methodology that I'm going to show you later in the presentation relies heavily on the class of semi-linear stochastic partial differential equations. And the second reason that we consider semi-linear SPDEs is that this incorporates a wide class of stochastic partial differential equations, which I'm going to show you in numerics. So for example, this could include a linear SPDE, also an SPDE where we have a trigonometric term defined by f, but also the Allen Cahn equation, which is a well-known stochastic partial differential equation as well. So these are the two underlying motivations why we consider this class of SPDEs. And as many of you know as well, if we consider this class of SPDEs, what we can do is represent the solution as a mild solution, which is just given by the very bottom representation that we have right here. And when I say mild solution, what I mean is the solution to this SPDE in the strong sense, but considering but also given that we're considering an infinite dimensional setting or setup, this is generally why we use the term mild solution, because we do consider strong solutions, but as well as this, we also consider an infinite dimensional setting as well. And as a result, we can consider this mild solution, which is well known. So if you consider a stochastic differential equation, which looks very similar to this instead of an SPDE, then many of you know that you can actually express the solution very similar to this expression that you have right here. Yes?
We would have a quick question from the audience.
Yeah.
So your this mild solution here, what does the equal mean? You see, in which sense is it equal? So it's almost sure. So it is in probability it is almost sure, but in space-time it is what?
In space, it's in the Hilbert space norm, the equality that you should interpret, and in time, it's for all times.
Okay, so in which sense? So pointwise in time. So it's C0 in time with values in the domain of A, or
Pointwise in time and in the domain. I forget.
Belong to H, the Hilbert space that we're looking at. So you should interpret the equality in spatial sense in terms of in the H norm.
it's in C0 in time and in H, yeah. C0 and 0t with values in H. So, okay. B. Color-Can will be interesting.
Okay, so we can continue.
You can continue, okay. So again, this is the general setup that we have for the stochastic partial differential equations. And of course, we have to discretize these class of stochastic partial differential equations. So what we are going to consider is a class of Galerkin-based solvers for the actual solution, which we denote by U of n of t. And so our motivation for using Galerkin-based solvers is that they are known compared to finite element methods and finite difference methods to have better convergence properties. But as well as this, again, to motivate the methodology that we are using is actually a Galerkin-based solver as well. So this is the reason that we specifically use these types of solvers. And the particular methodology that I want to motivate now, which is what the strong pairwise couplings are based on, is really the Exponential-Euler method, which was introduced by Jensen and Kloden in the paper that I showed you at the very beginning. And the key idea behind using this methodology compared to well-known existing methodologies, which they motivate in their paper, is to establish improved rates of convergence while breaking this barrier that they so-called say for SPDEs. So I believe the rate of convergence that they were able to get was about a sixth for well-known methods, but they were able to improve this to a third. And so if I was able to write this expression, if I was able to express the actual exponential-Euler method for this particular notation that we're using, it's essentially given by this equation that you see right here, which takes a very similar representation to the actual mild solution that you see right here, but there is a difference in this particular term that they have right here. So they use the ideas of exponential integrators in order to actually propose this exponential-Euler method. And as I've stated from their central idea, they are able to show improved rates of convergence. And with this, what you can also do is that if you actually define your solution to the SPDE given by this, then one can modify the recursion as this expression right here, where you can think of this as being the reaction term. And then because we're dealing with the actual Brownian motion and the actual increments itself, we can actually represent this in terms of a distribution given by this normal distribution or Gaussian distribution that you see right here. So given that we have this recursion, which we're going to use later for the actual coupling, I want to present the main theorem given by Jensen and Kloden, which is essentially this particular bound right here. So provided sufficient assumptions hold, I didn't provide the actual assumptions in this presentation because there were quite a few, and I didn't want to waste any time given the time constraint of this presentation. But if anyone is interested in actually reading these assumptions, you can find them in the actual paper itself. But let's assume that these assumptions hold, then what they have is this particular bound right here, where they have a bound on the spatial discretization given by this, And they also have a temporal discretization given by this right here, where J corresponds to the actual discretization related to time, and N corresponds to the discretization in terms of space that they have right here. And chi right here is just the particular constant that they have, which is between 0 and 1. And again, where U is the mild solution and V is just the actual scheme that they have right here, expressed as this. So this, compared to well-known methodologies, demonstrates improved convergence rates. And this is the actual motivation that we have for this particular strong pairwise coupling. And not to go back to the very beginning, this is the actual motivation again for the original paper that you see right here, where they use these ideas to apply it to multi-level ensemble Kalman filtering ideas. So given that we're going to use and exploit this exponential-Euler method, before I get into actually using this and describing the various couplings, I wanted to describe some works that have been done for multi-level Monte Carlo and its application for stochastic partial differential equations. So as I highlighted before, to the best of my knowledge, at least numerically, very limited work has been done on this particular bridging between these two various areas. Again, just to stress, most of the work, according to what I've seen, has been done on random PDEs, where you just assume, for example, that a diffusion coefficient is random rather than actually having a stochastic PDE. And so some of the work that we read based on what had been done was work done by Barth, Lang, and Schwab, which was published in BIT in 2013. But one key difference that they have compared to the work that we are doing or proposing is that I believe they consider actually a finite element analysis instead, where we're using a Galerkin-based solver. And if we consider the actual methodology that they have, what we can say is that if one is trying to target an MSE of order epsilon squared, one generally can attain the cost or the actual complexity rate, which is epsilon to the -3. So this is the interpretation that we had from this particular paper as well. And given how this was really the only paper that we could actually come up with some interpretation related to the complexity analysis, we felt that perhaps by using the actual scheme by Jensen and Kloden, that hopefully we could get an improved rate of convergence. But as well as this particular paper by Barth was specifically and only theoretical. And again, our motivation was to see if we could actually do some actual numerical experiments to highlight this improved rate of convergence if we were able to attain it. So based on this and based on what we've done in the paper, what I'm going to introduce now is 3 particular couplings that we have for the multi-level Monte Carlo for stochastic partial differential equations. And the various 3 couplings that we consider are going to correspond to the correct coupling, which is going to be related to the exponential-Euler method and what Jensen and Kloden do, as well as the naive coupling, which looks very similar to this but is different, and also a CM coupling, which is based on the Crank-Nicholson scheme for partial differential equations or stochastic partial differential equations. And so with this, for the correct coupling, what we're interested in is actually a pairwise coupling, which I denote by U of L j plus 1n, which is essentially this coupling that you see right here. And what we can do is actually attain this pairwise coupling through the actual noise itself. So if you recall, the noise was related to the reaction term that I showed you earlier on. And if we consider the reaction term on the coarser level, of course, you can also define it on the finer level, but if we define it on the coarser level, we have this term, which looks very similar. And recall that this Qn comes from the Qn, this Qn, the square root of Qn comes from the Q Wiener process. Then what we can do is just define it as this. And then, of course, using the methodology, we can just express it as this particular term right here. So therefore, by doing this, this actually yields a particular form for this reaction term, which is just given as this right here, where this is actually considered for the finer levels. And the key difference that we have here compared to what I'm going to show you later on is that we have this exponential term, which of course comes from the exponential-Euler method. So this is what I'm going to refer to as the correct coupling when I show you the numerical experiments later. The next coupling that I'm going to show you is what we call the naive coupling. So the naive coupling, if you look at it, looks very similar to what we have for the correct coupling, except the only difference that we have is that we don't have this exponential term at the very front of this particular term right here. And as a result, if we consider the naive coupling, initially before running the experiments, we pondered and believed that this would actually perform worse, hence the name naive coupling. Because as I've mentioned for the reasons below, this would not actually satisfy the telescoping sum property if we assume a nonlinear f for the semi-linear stochastic partial differential equations, but also as a result, this would result in a lower strong rate of convergence compared to the correct coupling. And the very final coupling that we just wanted to consider to really add another one was based on the Crank-Nicolson scheme, which we call the Crank-Nicolson coupling, which is just given through the usual Crank-Nicolson coupling that you see right here, the Crank-Nicolson scheme, given through this coupled course solution U of L. And therefore, if we actually define the actual coupling for the reaction term, we can define it very similar to the naive coupling, where we get pretty much an exact same expression that you see right here. So as a result, based on what I've shown you for the naive and Crank-Nicolson coupling for these particular terms, we can expect at least that the rate should be very similar for these particular couplings, at least compared to the correct coupling here. So with this, we provide the main theorem or the main result related to the work that I've basically just shown you. And rather than going through all of the details of this complexity analysis, I want to highlight that what we have are some key and subtle differences that we have here. So if you look at these three properties, which is what we would usually have in the multi-level Monte Carlo complexity analysis, there are a number of key differences. So if we consider first the variance term, we have this particular difference, which is given by L plus 1 squared, which you can think of as being some log factor. And given that we have this, and also given a few other aspects, we also have to consider this delta, where delta is greater than 0, because we have a faster decay rate that you see right here. So the variance is going to, of course, decay faster. And so as a result, one would expect that the MSE to actually be of a lower order compared to the usual MSE of order epsilon squared. So as a result, what we introduce is a delta greater than 0. And as a result, we have the MSE where we're interested in targeting not epsilon squared, but instead epsilon to the 2 to the minus delta. So this is now the MSE that we're trying to target. And if we're trying to target this particular MSE for a low choice of delta, then the actual cost to achieve this and the complexity rate is given by either this first one, which is slightly worse, but also if we consider the case of chi being greater than or equal to a half, we have epsilon to the minus 2. So this is an important point that I want to make, because essentially from this complexity theorem, we have two particular choices. Either we try to target an MSE, which is of order epsilon 2 to the minus delta for all couplings, and then if we consider this case, we should be able to actually achieve the canonical rate of convergence. But given how this may be a slightly worse way, or not a good way of doing this, instead what we can also do is try to say, for the numerical experiments, which I will show you, let's say we're going to try and target instead an actual MSE of order epsilon squared. And as a result, if we consider to try and target an order of epsilon squared compared to epsilon 2 to the minus delta, this complexity rate that we see right here is not going to hold. And as a result, we should, in theory and also in practice, be able to see a slightly worse complexity rate compared to epsilon to the minus 2. So we have these two particular choices what to do, but I'm going to tell you that for the numerical experiments, we're going to consider the latter, which is to say we're going to consider targeting an MSE of epsilon squared. And as a result, this complexity rate will not be exactly this, but it will be slightly worse than this, but still an improvement over the other two couplings if we consider the correct coupling. And also just to say, this theorem is also specific to the case of using a linear operator A, and also I believe a linear operator F as well. So this theorem only holds for the linear stochastic partial differential equation. This is not the case for using nonlinear SPDEs. For F, which is what I meant to say. So just before I get on to the numerical experiments, we have a number of results which are not exactly proven, but at least they are conjectured based on what we can see from the numerical experiments, which is that we have the following conjecture for the stochastic Crank-Nicolson coupling that we have. And this bound is very similar to the bound that I showed you earlier for Jensen and Claudin based on the Exponential-Euler method. And as you see, for the spatial discretization, it looks pretty much identical to what we have before, but the only difference that we see is through the temporal discretization. So what we had for the correct coupling was log j over j, but now we actually remove any notion of this logarithmic term, and instead what we have is just this j term. So this is really where the difference you can think of lies between these two particular schemes in terms of this particular bound as well. And so from this conjecture, which we haven't proved, but from this particular conjecture, we have the following corollary, assuming that it's true, which is to say that if we want to achieve an MSE of order epsilon squared, then we have this particular complexity rate for the Crank-Nicolson coupling, where we can achieve the actual canonical rate of convergence, but we're more limited than the actual choice that we have. So this choice is specifically between 3/4 and 1 compared to the previous rate that I show you, which is that we can achieve the same rate for this, however, but this is where we have this particular better choice of the if statement, where chi is greater than or equal to 1/2, as opposed to between 3/4 and 1. And so to show you the improvements for the correct coupling, what I am going to specify is the particular case of chi equals 1/2. So if I choose chi equals 1/2, we should be able to achieve a slightly worse rate than epsilon to the -2 for the correct coupling. But for the Crank-Nicolson scheme, because we're choosing chi equal to 1/2, we should be able to achieve this rate. And if we actually substitute 1/2 into this, then what we're going to get is actually epsilon to the -3 is the actual complexity rate. So now let's get on to the numerical experiments, which I'm just going to show you very briefly. Again, the class of SPDEs that I'm going to consider is this semilinear stochastic partial differential equation with this prescribed initial condition that we have right here. And so with this stochastic partial differential equation, as I mentioned, this can incorporate a wide class of SPDEs. And the 3 SPDEs that we actually consider in the actual paper are given based on the actual choice of f. So if we consider f of ux to be u of x, then of course this is just a linear reaction term, and therefore what we have essentially is just a linear stochastic partial differential equation. As well as this, we also choose this choice of f, which is a trigonometric reaction term, and therefore we also test this, which is our first nonlinear reaction term. And finally, the last reaction term we consider is this, which actually corresponds to the Allen Cahn equation. So all of these 3 stochastic partial differential equations that you see are tested in the paper, but what I'm going to show you in this presentation is essentially just highlighted in blue and red. I'm only going to show you the numerical experiments for u of x, and I'm also going to show you the numerical experiments for this as well. And finally, just before we get on, I'm just going to state that the actual choice of lambda n and q of n are just given as this. So q of n is generally given by lambda n to the minus chi, but if you recall what I stated here, we actually choose chi to be 1/2, so that's why we have this particular choice of the actual exponent for lambda n for the q Wiener process that we have. So the first figure that I'm presenting here is essentially the couplings between the final level and the coarser level, where the final level, I believe, is given in blue and the coarser level is actually given in red. And we have a comparison of all of these different couplings within each of these different rows. So the columns correspond to the different couplings, and these actually rows correspond to different choices, I believe, of J. So these particular rows are fixed for the choice of capital N, which corresponds to the spatial discretization where n equals 50, I believe, or n equals 100. But what we have here on the first row is J equals 25, J equals 50, and J equals 100. So this is for the linear reaction term, and as you can see from this coupling already, there's not a huge difference in terms of what we see by increasing the actual level of J. There isn't a huge difference. They all start to behave more or less the same, as we have a very fine level of J where they look very similar. But if there is any observation that you may say is that for the correct coupling, there is a slight improvement compared to the other two. But given that this is a linear SPDE, we would expect the difference between these couplings wouldn't be so huge. So this is just to give you an idea of how these couplings are actually different within modified versions of J and N. And so with this, I'm going to give you 2 figures on this particular slide. The first figure that you see at the very top is essentially approximation, or the multi-level approximation of this black dotted line for various choices of the MSE. And so this is the correct coupling, this is the naive coupling, and this is the actual Crank-Nicolson coupling. So as we go from the correct to the other 2 couplings, we start to see some fluctuations around this actual line that we're trying to approximate. So this gives us an indication that with the correct coupling, irrespective of what the MSE is or what the tolerance level is, we start to get a very consistent approximation compared to these other 2 couplings. And then finally, the very bottom figure really highlights what I was telling you, which is related to the actual complexity analysis between the tolerance level and also the cost. So if we consider the correct coupling, which is given by the solid black line, we actually don't see the actual canonical rate of convergence because, like I mentioned, we cannot expect to achieve this considering we're actually targeting an MSE of order epsilon squared. So what we do get is actually the complexity rate which goes beyond epsilon to the -3, which is log epsilon squared epsilon to the -2. And if we actually look at the other 2 couplings given by the naive coupling and the Crank-Nicolson coupling, the rate that they have, of course, matches the theory that we have, which is order epsilon to the -3. So this is for the linear stochastic partial differential equation, which includes a linear reaction term. And then finally, if we just consider the numerical results for the Allen Cahn equation, the coupling difference that we see between all of the different couplings for the different levels of J from 25, 50, and 100 are more apparent. Of course, there's bigger differences between low levels of N and low levels of J, but as we increase to J equals 50 and also J equals 100, we start to see that the coupling difference, or the difference between the coarser level and the finer level in the multi-level setup, is virtually identical for the correct coupling compared to that of the naive, and also compared to the Crank-Nicolson scheme. And then finally, these are just the exact same plots that I showed you before, where the approximation in terms of the multi-level estimator looks the best related to the correct coupling compared to the naive, and also the Crank-Nicolson. But also, if we just look at the tolerance compared to the cost, we start to observe pretty much the exact same rates as before, which is to say that if we use the correct coupling, we do achieve an improvement over epsilon to the -3, but with the naive coupling and the Crank-Nicolson coupling, we of course achieve order epsilon to the -3. So again, even though the actual theory that we have is not specific to this particular case of an SPDE, it is still promising to at least say that by actually testing this methodology on these numerical models, such as the Allen Cahn equation, we can observe similar rates of convergence and also similar actual results compared to the linear SPDE. So to conclude, again, this motivation behind the presentation was really to try and get a better understanding of the application of MLMC to stochastic partial differential equations. There has been limited work done on this, and we wanted to bridge this gap between these two areas and try to get an understanding, at least numerically, what could be done and what could be observed anyway, despite having no particular theory for this. And what we motivated through this was the Exponential-Euler method, which had already been tested for the multi-level ensemble Kalman filter. And what we wanted to do was to actually use this methodology for stochastic partial differential equations, where we were able to show a complexity theory related to the linear case, which demonstrated that we can get improved rates of convergence. And we actually showed numerical evidence related to this for both linear SPDEs, but also other known SPDEs, such as the Allen Cahn equation or the Allen Cahn SPDE. So given that we have done this work, I believe there's a number of very interesting directions to consider from this. Related to the theory, it would be interesting to see that if we consider a nonlinear F, could we still attain the actual same complexity results that I showed you, or perhaps even different ones? It is not so obvious what the actual rates would be, and I think requires a lot of delicate analysis in order to do this. I believe this is one of the reasons perhaps why this has not been done in the literature, because it is quite challenging and it is difficult, but at least would be interesting, because having theoretical results related to this can also help motivate particular applications, which relates to the second point, which is that can we consider more realistic models or other SPDEs, such as stochastic Burger's equation, or even the stochastic Navier-Stokes equation? And this is a very common model which is used in both forward and inverse UQ theory. And I think this is a very next natural stepping stone to consider these particular applications. And then a very final consideration to actually work with is actually a framework for multi-index Monte Carlo. So this is a typo, it shouldn't say multi-level, but given how we've worked in the multi-level setting, could something be done in the multi-index setting? Of course, this can be quite challenging, because in order to exploit multi-index Monte Carlo, one has to assume a very high regularity or smoothness related to the actual differential equation. And of course, given that we would have to have these strict assumptions, and of course, given how it may be helpful to actually derive theory for the nonlinear F, I think this is a very challenging problem, at least for the nonlinear case, but given if one could do this, I think would be very promising indeed. So this concludes my presentation for today. If anyone has any questions, I'm more than happy to answer them. And if anyone is interested in reading more on this, I would highlight them to this particular paper that we have. So thanks.